So we were able to calculate the friction factor for laminar flow, but for turbulent flow, we're not going to be able to do it that simply. We're going to have to rely on basically empirical relationships, that is, relationships that are based on experimental study. What they find when they look at the friction factor for turbulent flow, they find it depends on three things. It depends on the channel or pipe geometry. That shouldn't surprise you. It's a round pipe, an open channel, flow between plates. Those are all going to have different friction factors. It depends on the Reynolds number, which obviously at this point I don't think will surprise you either. We've seen the Reynolds number keeps cropping up in these types of problems. So it's going to depend on those two things. It's also going to depend on surface roughness. So this is the actual roughness of the surface of the pipe or the channel. So this might be a little bit surprising because we haven't seen that before. And of course, real surfaces aren't perfectly smooth. They have bumps on them. And when you have laminar flow, it turns out it doesn't really matter unless the bumps are extremely large compared to the scale of your flow, or large compared to the scale of your flow field. The flow near the wall is going exceedingly slowly. The wall flow on the wall is zero, of course. The velocity is zero on the wall, no slip condition. So the flow going just over the top of these bumps is moving extremely slowly. The flow doesn't, the fact that there's a little bit of bumping doesn't really change anything. And the flow just goes faster and faster as it gets farther and farther from the wall. And by the time the fluid is moving fast, it's really far beyond these bumps, and these bumps are irrelevant. That's what happens in laminar flow. But in turbulent flow, you have these swirling eddies, and they bring very fast moving fluid down into contact with the bumps. And it turns out that that really can change the frictional effect. So when you have fast moving fluid slamming into these bumps, it changes the shear stress. And bigger bumps will cause more shear stress as more and more fast fluid is brought in contact with the wall, basically because there are more bumps for it to run into, more surface area for it to interact with. So that's what essentially causes the surface roughness to matter for these turbulent flows, is the fact that fast-moving fluid gets slammed down into these bumps, and that means the bumps actually do have an effect on the shear stress. The fluid's not just all moving really, really slowly across the bumps, or almost not moving at all across the bumps. So the surface roughness is a new characterization. It depends on the material used for the channel or for the pipe. It's characterized by an epsilon. This is the surface roughness. And the surface roughness, as I say, depends on the material that the pipe or channel is made out of, and it's basically the size of the bumps. So different materials have different levels of smoothness, and depending on those bump sizes, that can really affect the frictional effects along the wall if the flow is turbulent. Here's an example of I'll just put this piece up. Hopefully we can see it well, it's only in pencil. So here's an example of some different materials and their surface roughness. So here's, if you look at sheet metal, this is sheet steel. It's got a 0.05 millimeters. So that's pretty small. It's half a millimeter sort of bumps. If you have stainless steel, it's even smaller. Nice smooth finish there. 0.002. Cast iron, of course, is rougher. We've all touched that. It's a 1/4 of a millimeter, quite a bit rougher. Glass is really smooth. So glass is truly smooth, and a glass pipe can be treated as a perfectly smooth surface. And wood, of course, is the roughest of these examples. But the point is, this is something you would have to look up. You would have to, based on what material is used for the material, for the pipe, or for the channel, or for the plate, they would have different roughnesses. So it's just a property that you have to look up in order to get it. So finally, you need a relationship for F. So if we got those three things, there is a relationship that relates those three characteristics to the friction factor. Here's the formula. It's called the Colebrook equation. And here's what it is. It's 1 over the square root of F is equal to minus 2.0 times the log of the surface roughness divided by the diameter of the pipe divided by 3.7 plus 2.51 divided by the Reynolds number based on the diameter of the pipe and times the square root of F. So that's the Colebrook equation. It depends, as I said it would, on the surface roughness, the Reynolds number, and the geometry. The geometry comes into play because of the diameter of the pipe. And so though this is a basically impossible equation to solve. You can't solve this for F. You have to put in different values and develop correlate. You can solve it with computers. You can't solve it by hand at all. There's no real way to explicitly solve it for F. F is in the denominator here. It's in the denominator here. There's no good way to turn it upside down. So this equation is true, but it's not very useful in this form. I mean, you can generate useful results with it, but you can't really use the Kohlberg equation. But what people do with the Kohlberg equation, we'll see, is they turn it into a graph or a chart that you can use. So this equation leads to something for the friction factor that is in fact very much like the steam tables are for your steam property. Something that, yeah, this exists, but you're not really going to use this, but this leads to something that you can actually use.